everyone. This is the second class of this week. In the last class, we derived the governing equation in terms of stresses, and the another part of the boundary value problem is the boundary condition. And today we will see how the boundary conditions to be written, and then what is the form of that boundary condition and what information we can extract from that form. Okay. So, if you recall, if this is a problem, then what we are interested in, what the problem description is, this is subjected to a torsion, suppose a torsion like this, okay, at this boundary. Now, this has, when we say boundary conditions, means all the boundary we have to specify the conditions. What are, how many boundaries we have here? One boundary we have is the both ends of this, means the on the cross section where the torsion is being applied, this is one boundary, and another boundary is at z is equal to 0, which is at this point. So, these are two boundaries, two ends we have. Suppose these ends are denoted as R, and then between these two ends we have the surface of this solid, and suppose this surface is S. So, when we write boundary condition, we have to specify boundary condition both on S and R. Let us start with S, and then we see what is the boundary condition on R. So, if we take a cross section like this cross section, and this is the cross section like, and then this surface is S. Now, look at this problem. By just looking at the problem, we can say the boundary conditions are, what is the boundary condition on S? The S is a stress free boundary. So, we do not apply any external load or external pressure on this surface. So, essentially it is a traction free boundary. So, if we have a traction on this boundary, this traction will be 0. This traction on this boundary will be 0. Now, what we have to, we are going to do now is we are going to see how this information to be written in terms of mathematical equation. Let us do that. So, take any section. For instance, if we take a section here, take any section. So, this is the corresponding section, and suppose this section, this distance is dx, this distance is dx, and this distance is dy. To be precise, this distance is minus dx, because x is in, it is in other direction to x. Okay. So, and suppose this is the unit normal, this is n, which define this plane, and then this has two components, one is the horizontal component and one is the vertical component. So, this is ny and this is nx. So, n is essentially an unit vector. In 3 dimension, it has nx, ny, nz, but now we are just taking a section. So, it is essentially on a plane. So, we have nx and ny. Now, so how this nx and ny is related to each other? We can write the relation. If this distance is s, if suppose if we have this is S, the entire surface is S, and then we can write nx as, nx is equal to dy by ds, and similarly we can write ny is equal to minus dx by ds. The minus, because this distance is minus x, it is in other direction. And then what is nz? Nz in this case will be 0, because we are taking just a plane. So, there is no nz for this. So, this is the components of n, right. Now, once we have that, if you recall how we define traction on a plane, traction is defined as, suppose on this surface, if the traction is this is traction, suppose Tn, then Tn is defined as, Tn, if you recall, that is equal to sigma dot n. So, sigma is a second order tensor, is a Cauchy strain tensor, and then T and n, T traction is a vector. Okay, this is the traction, this is the stress on this or the traction at this point. Now, since this is a stress free boundary, there is no traction on the boundary. So, there is no external load on this boundary. So, naturally this has to be 0. So, this is the boundary condition we have. Okay. Now, let us see, let us expand these equation, let us write traction in terms of their components and then see what this information, how we can simplify this expression. Now, if we do that, so let us you recall this is the expression for traction in terms of stresses, and we also recall now what we have is from this we have nz is equal to 0. Since nz is equal to 0, so all these terms straight away we can make them 0. Okay. And then in addition to that, what information we have, recall in the last class we discussed for the chosen displacement field, we have these stress components are 0. If these stress components are 0, then straight away we can make some of the quantity from this expression, we can straight away make them 0. So, sigma xx will be 0, and then sigma yy will be 0, sigma zz will be 0, and then sigma xy will be 0. So, this will be 0 and then this will be 0. So, essentially what we are left with, we have then what we are left with, let us write that. So, what we have is now then we have traction as only z, because all the among 3 equations, 3 components of traction, traction in x direction, traction in y direction, they become 0, because the corresponding stress components and the components of an nz is equal to 0. Eventually, we are left with the third. This is the component of traction. Now, again recall the expression for nx and ny. Just now we derive nx is equal to this, ny is equal to this, and nz is equal to this. And if we substitute that in this expression, then what we get, and before that we recall the stresses are written in terms of a stress function psi, and this is the relation between the stress function and the corresponding stress components. What we do is now we substitute this information and this information into the first equation, and then what we have this expression. Okay. Now, this expression is essentially, we can simplify this as this. So, this is important. So, what you see, what it says that so what we can write, if this is equal to 0, then if I have to integrate it, so then this integration will be psi is equal to constant on S. Remember, psi is not constant everywhere, since at the surface, in this case it is S, it is the traction free boundary, and when we substitute, when we impose that boundary condition, and when that boundary condition is written in terms of psi, what we get is psi has to be constant on the surface. Now, constant means, so you can take any values, but for general practice, at least for a simply connected domain, we can assume psi is 0. Just to give you an example, suppose we have a domain. For instance, we have a domain, suppose a circular domain. Okay, take a circular domain of, say, radius is a, radius is r. Okay, or take a. Radius is a. Then what is the equation of this circle? Equation of this circle is x square plus y square is equal to a square. Let us assume psi is equal to x square plus y square minus a square. We have to start with an assumption of psi, right, very similar to this Airy stress function. We assume some expression of phi which has certain constant, and then those constants are determined through equilibrium equations, through the governing equations, and also the boundary condition. Similarly, here also you have to assume some expression for psi. Now, if we take this assumption psi, you will see that psi is 0 on this boundary. So, psi vanishes on this boundary, which is consistent with this definition of psi. Now similarly, if we take an ellipse, suppose the cross section is an ellipse which is defined as x square by a square plus y square by b square is equal to 1. Now if I take psi is equal to x square by a square plus y square by b square minus 1, and then what happens? Psi vanishes at the boundary, and then it is also consistent with this expression. So when we in the next class we'll solve these two problems. One is shaft with circular cross section and the shaft with elliptical cross section. There this point will see what is the advantage of taking psi like this as the outer surface of the cross sectional profile of the section. Okay. So this is the condition that to be satisfied on the surface. Now once we have that, let's move on, and then next is let us then apply the boundary condition on the two ends. So if we apply boundary condition on S, that boundary condition essentially reduced to a condition, and that condition says that del psi del s d psi ds has to be equal to 0, or the psi, which can be interpreted in this way, psi is a vanishing function on the surface. So this is the first boundary condition on the surface. Now let us write the boundary condition on two ends. Okay. Now how do we define two ends are essentially your plane, and how do we define those planes? This is the normal vector, and suppose this normal vector nz is equal to 1. Now on this plane and on this plane nz is equal to 1, then on this plane it will be nz is equal to minus 1, and nx and ny will be 0, because this is normal to this plane, this is normal to this plane. Okay. And then we have nx and ny is equal to 0. Very just look at the difference between when we apply boundary condition on the surfaces. Nx and ny were non-zero and nz was 0, but now in this case when we apply the boundary condition at both ends, we have nx and ny 0 and nz is plus minus 1. Okay. Now if it is, now let us recall, now this is the expression we have on the traction. Now before that let us find out what are the boundary we have on this surface. Now let us on this surface what we have, we can have a force in this direction, suppose that is force Pz. We can have force in x direction, we have Px, and we can have force in y direction, which is Py. Similarly here also we can have force in x direction, which is Px, and then we have force in y direction, we have Py, and force in z direction we have Pz. So we can have three forces. I am just writing a most general case. For a torsion we do not have actually Px, Py, Pz, they will be 0, but whether this condition, whether it is automatically being satisfied or not, or what information we need to impose to satisfy this condition, we have to see that. So these are the very general case. Now in addition to that, what are the things we have? We can have moments also. So we can have say moment, we can have moment about x axis. About x axis means we can have moment, this is mx. Similarly we can have moment about y axis, which is my, and we can have moment about z axis, which is mz on this surface. Similarly on this surface we can have moment about z axis, which is mz, and then moment about x axis, which is moment about y axis, x axis, which is mx, and then moment about y axis, which is my. So at every boundary at both ends we have three forces and three moments. Okay. Now how do we represent say force? Let us find out. If I have to write the force in terms of stresses, if I write to what is the expression for Px? Expression for Px will be that now on this surface, suppose Tn is the traction, and Tn has three components. One is Tnx, then Tny, y, and Tnz. Okay. So, essentially Tx, Ty and Tz are the components of Tn in xyz direction. Now, if I have to write what is Px, then Px will be this traction is defined at a particular point and this traction has to be integrated over the entire area, we get the total force in x direction. So, Px will be integration over the entire area R and then Tnx x component, and this will be dx dy, this will be the component total force in this will be the force in x direction. Similarly, if I have to write out force in y direction Py will be integration over the entire area I, component of traction in y direction, integration of that. So, this will be Tny dx dy, and then similarly Pz will be integration over R, or R means the entire area, and Tnz dx dy, right. And this is true for this and this. Now, both the ends. Similarly, if I have to write say moment in a particular direction, then the moment will be, say let us write the expression for moment z. Moment z will be what? Now, what are the components? What are the component of forces which will contribute to the moment? Py will contribute and then Px will contribute. It means that Tx will contribute and Ty will contribute. So, moment will be Tx into multiplied by y integration and then Ty multiplied by x integration, and this will be integration over y, then x into Tny, the y component of the traction, minus y Tx x component of that traction, that is integrated dx over this. Okay, this will be mz. Now, if I have an external force, say externally applied torque at that end, at the considered end is T, then this has to be equal to T. Okay. Similar way, we can write expression for mx and expression for my. Okay. Now, what are the boundary conditions we have here? My. Look at, we only have the boundary, this is a general case. Now, if we reduce this, if we now consider only the case we have in our hand, where we have a shaft, and on that shaft at one end we are applying only torsion. Okay. Now, in that case this will be equal to 0. There is no external force being applied in x direction, because there is no extension or stretching we are considering in this case. There is no force in y direction, there is no force in z direction, all these forces will be 0. Now, let us see the moment. Only moment being applied at this section is about z axis, which is the torque, but no other moments being applied at this end. So, mx will be 0 and my will be 0. So, these are the boundary conditions, or traction boundary condition. The entire thing is the traction boundary condition we have at the both ends. So, total 6 condition. All the forces are 0, mx and my are 0, and the mz will be the externally applied torque. Okay. So, now let us see what is, so if I write it, then what is the expression we have. Now, this is just recall, this is the this is the this is the expression for torsion, this is the expression for traction, and if we substitute these conditions nz and nx is equal to 0, essentially we have these components are non-zero, this is 0 component. Okay. In the previous case, when we apply boundary condition on S, only Tz was non-zero and Tx and Ty were 0. Okay. Now, then what would be the conditions? Conditions will be, you recall, these are the conditions just now we wrote. Okay. These are the force, and these all these force and moments will be 0, only is this is non-zero. Now, let us see. So, we said that this is the condition, right? This is the boundary condition needs to be satisfied. Now, the way we define stresses and then traction, let us see whether that definition is consistent with this boundary condition or not. We will prove it or do that exercise only for the first case. and the other case we can apply the similar way. Okay. So, first case is this is the expression for P x. Okay. Now, if I substitute the expression for torsion, expression for T x, and if you look at T x was how much just in the previous slide, if you T x was sigma plus minus sigma x z. It plus and minus depends on which end we are considering, at a z is equal to 0 or z is equal to or n z is equal to minus 1 or n z is equal to plus 1. So, but the main thing is that tau x t, the component in x direction is sigma x z. Okay. So, let us write that. So, this expression becomes, this is equal to so if I write this as plus minus, so this become plus minus integration over r, this is sigma x z, just now we have checked sigma x z, and then this integration is over dx and dy. So, this has to be equal to 0. We do not know whether this is equal to 0 or not. This is P x. This condition needs to be proved, the first one. So, this is the P x. Okay. Now, let us substitute sigma x z by the definition of the stress function. So, this become plus minus integration of r over the entire cross section, and this becomes del psi del y, and then dx dy, right. Now, here if we apply Green's theorem already discussed in when the concept of tensor were discussed in the second and third week, Green's theorem was discussed at that time, and if you recall that Green theorem, if you apply Green theorem, then this becomes this integration over, it was integration over the area, and this becomes integration over the boundary. This integration over the boundary, this is a closed integration, and this becomes psi n y ds. Okay. So, essentially it project integration from area to line, or from solid to surface. In this case, it is on the area and it is on the boundary of the area. Okay. So, integration is being projected on the boundary. So, this gives. Now, look at, just now we discussed what was the condition when we applied, condition that we obtained when we applied boundary condition on S. The condition was d, if you recall, the condition was d psi ds is equal to 0, which gives psi is equal to some constant, and we said that this constant, for simply connected domain at least, this constant you take 0. Means psi is chosen such that it vanishes at the boundary, and if it vanishes at the boundary and this integration is over the boundary, straight away it becomes 0. Okay. So, this is proved. Okay. So, by choosing psi which vanishes at the boundary, automatically all the boundary conditions that you have, the traction boundary condition you have at both the ends, are satisfied. Okay. Now, so this exercise you can try for other component also. So, this condition you can similar way you can show the other boundary conditions also they satisfied. So, these are all boundary conditions. You can do the same exercise and then check whether the definition of psi, the chosen definition, the way we are choosing psi, if they satisfy these boundary conditions or not. Now, in this case we are now interested only on the last part, because that gives you the relation between the externally applied torque and the internal stresses. Now, let us see the last one. Now, last one is this is the torque, expression of torque that we have. Similarly, we substitute the expression of Ty and Tx, and then if we substitute that, and then substitute those stresses in terms of the stress function, then this is the expression we have. Now, this integration is this integration has two parts. Let us see what are the first part comes. The first part is this. Now, if we integrate it by parts, this one, then this integration gives you this. Okay. Now, from this take this part, if you apply the Green's theorem, the way we apply Green's theorem just now, if you apply Green theorem, I mean projecting this integration on the boundary, and this expression becomes this, okay, and this will remain as it is. Now, similarly, if you, so this, the first part, the expression becomes this. Similarly, if you take, if you integrate the second part in parts and then apply the Green's theorem, what final expression you have is, this is your final expression. Now look at this expression. Again the same condition, phi is chosen such that it vanishes at the boundary. So this straight away this becomes 0. In this case also straight away this becomes 0. So and what this becomes? This is t is equal to, we are left with only this part and this part. Okay. So this part becomes then 2 into, if we add them, this part become 2 into integration over r psi dx dy. That becomes your t, and then we have a negative sign here. Okay. So final, your relation between the applied torque and the stress function is this. So this is essentially the last boundary condition. So let us quickly revisit everything and summarize all the equations. That summary is, you see, what we did is we started with this definition of displacement field, and the assumption was the small deformation, the displacement is small, and that is why the rotation can be taken as linear function of the longitudinal axis. This is the assumption, and this assumption gives you that rotation is a linear function of z, and when you translate that rotation, from that rotation, when you get the displacement corresponding in the different direction, we get u and v as this. And then another assumption we had is the out of plane deformation, we assume it is only a function of x and y, it is not a function of z. So this is the displacement field that we started with. Okay. Now that we discussed in the last class. Now once we have this displacement field, from that displacement field, what we did is we calculated the for this displacement field gives us some of the strain components 0 and some of the stress components 0. Then we define stress function. Stress function is how the stresses, the non-zero components of stresses, these are the two non-zero components of stresses, and how these two non-zero components are related to stress function. This is the stress function. Okay. So this, and then what we did is we substituted the stress function in the equilibrium equation and also in the compatibility equation, and combine the equilibrium and compatibility equation, and finally we have a Poisson's equation, and this is the equation, right. This is our governing equation. Now once we have the governing equation, next thing is we have to apply the boundary conditions. In this case, since it is a stress formulation, we have to apply the boundary condition on stresses, means we have to write traction boundary conditions. Now we have two boundaries, one is on the surface of this, or the surface of the shaft, and another is two ends of the shaft. And if we apply the boundary condition on the surface, then what we have is boundary condition on S, it gives you d psi ds is equal to 0, and this gives you psi is constant. We can assume this constant is 0, and which means psi vanishes on S. And if we take psi vanishes on S, we have just now seen that other traction boundary condition at both ends, they are automatically satisfied. And then if we apply the boundary conditions at the ends, the final expression that we have is this. So this is the summary of the equations what we discussed in the previous class and what we have discussed today. So this is the summary. Next class what we do is we demonstrate these equations, the application of this equation through two examples, and then we compare the results that we obtained from elasticity solution. We compare the results with the solution that we already had from strength of material, and then we see whether they are is there any discrepancy, and we try to understand what could be the possible reason for this discrepancy, and then we also apply these equations to some other problems in torsion. I stop here today. See you in the next class. Thank you.